Good afternoon, everybody. That was loud. You know, I'm always nervous when I come to speak around this time in afternoon. A couple of reasons. It's after lunch. It's after a few of very technical presentations. Many of us start feeling a little bit sleepy. Right? So if some of you are already feeling sleepy, get ready. Because I've got this God-gifted capability. When I speak, people feel really sleepy. So get ready for the ride of your life. My name is Kamran Naqvi. I work for Broadcom, based in the UK. My title is Chief Architect, but I'm an engineer at heart. And today I'm here to tell you a story from a network engineer's point of view. As a network engineer, how I see AI coming into my world, into our world of networking. What are some of the challenges I am seeing when I see these AI workloads? And what are some of the things we are doing to improve them? I will also talk about some of the enhancements we are doing in Sonic to cater for these requirements. And then I'll finish off by talking about why we think that Ethernet is the right network for AI workloads and how we are making it even better with Ultra Ethernet Consortium. So if you think about cloud computing, CPU was something which was used for cloud computing. But cloud computing was a virtualization problem. Would you agree with me? What we were doing there, we had a bunch of servers with CPUs, and we were trying to virtualize those CPUs and resources so we can run multiple virtual machines on the same hardware resources. Think about what we are doing with Gen AI. It is quite opposite. With these Gen AIs, these models, talk about ChatGPT-3, they are so large that you cannot run them on a single CPU or a single GPU. I mean, ChatGPT-3, how many parameters are there? Over 170 billion. ChatGPT-4, there are over 1 trillion parameters there. So these models are so large that we cannot run them in a single CPU or a single GPU or even a bunch of GPUs. You need to have these tens and tens of thousands of GPUs to run these models. So think about it. We are talking about one model that we are trying to run on thousands of these nodes. So essentially, all of these GPUs need to interwork, need to be interconnected, and they need to work together. They need to act like a single computer. So from this point of view, this AI networking is really a distributed compute problem. And in this distributed compute problem, our network is playing a key role because the performance of the AI infrastructure depends on the efficiency of your network. So network is the key element in this AI infrastructure, and I would argue network is the computer. And these are not my words. This was something coined by Sun 20 years ago. And they said, network is the computer, but that statement is still very true when we start looking at these AI infrastructures. This is a picture from a Google data center 15 years ago, where what I would say Google was trying to solve the previous generation distributed compute problem. What was that? Search. And how did they do that? They had all these servers. These are all bare metal servers running commodity CPUs, and they have thousands of those, and they connected them with open Ethernet fabric. And they did a very good job in solving that problem. But look at this slide. This is the slide from Alexei from Meta 2 years back from his OCP keynote. And what they're saying is, what Meta are saying is that network is the bottleneck in my AI infrastructure. Does it make sense? I mean, we said we solved that problem already. They are saying network is the problem. Now look at that. What they are showing here is, this is the time spent in networking for their various GPU loads. You can see in some of these cases, 57% of the time is spent in networking. If you add all of these, you will see that on average, 35% of the time is spent in networking, which means that for 35% of the time, those GPUs were sitting idle, doing nothing. They were waiting for networking to complete their job. I mean, you spent millions or billions of dollars to buy these GPUs, build this, state-of-the-art infrastructure, but for 1/3 of the time, 35% of the time, your GPUs are sitting idle, not doing anything, because networking is not doing its job. Remember I said, networking is the key element in this AI infrastructure. Now, networking is probably just the 10% of the cost of building an AI infrastructure, but if networking is not done right, it costs a lot more. So why that is the case? What is different about these AI workloads? That is what I'll try to explain in this slide. So point number one, when you look at cloud computing, you have small packets, small flows, and you have multiple machines talking to each other. Thousands of machines are talking to each other. When you come to AI infrastructure, you have very, very large flows, which means that they last for a very, very long time, and there is a lot of data that is being exchanged. These are elephant flows. And comparatively, there are less number of flows. So pay attention here. Less number of flows, and these are RDMA flows, which means that when you look at the 5 tuples, you do not see a lot of entropy. So less number of flows, RDMA flows. If you have low entropy, what happens? You do not have good load balancing. You are not being able to utilize all the links that you have. You see the problem? Second point, these RDMA flows, they are very sensitive to packet drop. Why? Because they run algorithms like go back n, go back 0, which means that if a packet drop happens, you will be seeing a lot of packets being retransmitted, because it depends on where the checkpoint was made. So a single packet drop may result in a large number of packets being retransmitted. Obviously, your communicate phase will be longer. And the last point I'll make here is this tail latency. Now, we are talking about machine learning algorithms. How they work, they have these compute phase, communicate phase, and the synchronize phase. In the compute phase, they are doing these matrix multiplication, and the outputs are your gradients and your weights. And then these outputs is exchanged with all the GPUs, who will then synchronize it. The next iteration will not start until the last GPU has completed its job. That's a killer point. Because just one slow flow will slow down everyone. Look at this graph. I'm partially colorblind, so I'm just using the colors which my wife said they are. I hope they are correct. So what I'm told is that this is kind of a brown type flow and the orange flow. These are the two flows which have completed their job. But look at this. The next cycle does not start until the last GPU has done its job. Do you see that? Once the last GPU has completed its job, then everyone is starting their job again. This is what we call tail latency. It is a killer for your job completion time. So how do we look in your network and identify what are the factors which are contributing to these problems, and then how do you resolve it? I usually take 1 hour to do this presentation. Today I'm going to do it in 20 minutes, so let's see how we go. Number one is transient oversubscription. We all know what oversubscribed networks are. We don't see them a lot in the, in the AI backend fabrics. You still might see some of them in the storage part of the AI fabric. So they are relevant, but not that relevant. So I won't go in much detail about it. Flow collisions and link failure. Now that is a big problem. Because what are flow collisions? When your static ECMP map multiple flows to the same link. We are talking about elephant flows. These very heavy flows have been mapped to the same link. Obviously, there will be congestion. So that's one issue. Second thing, link failure. When you have a very large network, link failures will happen. And remember I talked about that they are very sensitive. These applications are sensitive to packet drops. Link failure happens, packet drop happens, you have an issue. Finally, incast. Incast happens when multiple GPUs are talking to one GPU. Once again, obviously you don't have enough bandwidth to talk to everyone at the same time. How do you do congestion management? So let's talk about the solution one by one. First thing, time spent, first thing is your transient over subscription. We have some very good in-band telemetry feature in our silicon. If some of you attended my last year's presentation, I talked about these. My presentation was on in-band telemetry features. I don't have time to talk about it in detail here today, but I will refer you to a very good presentation done by Alibaba with my colleagues from Broadcom 2 years back in OCP. I have a link there for it. And where Alibaba talk about that they use these silicon-enabled telemetry feature in Broadcom silicon, and they improve their efficiency, they reduce their tail latency by 50%. Proof is in the pudding, right? I could do a demo and you will say what is the value. When a customer is here talking about how they've resolved their real life problem, you can see that this technology works. They talked about this Double 11 festival they have in China, which is like Black Friday here, right? Where they saw a lot of improvement in their, on the Alibaba website, and they saw a lot less problems. Okay, how do you resolve this flow collision problem? Very simple answer. You need perfect load balancing. How do you get good load balancing? I'm talking about two approaches here. On the top, you go with a packet spraying approach. Even for one flow that you're receiving, you do a per packet load balancing. You spray all the packets across the available link. That will give you a perfect load balancing. Would you agree? Yes, it does. What is the problem with that? The catch is reordering, right? On the receiver side, packet will come out of order. So you need to have this reordering capability on your receiver side. The second approach here is about what we call cognitive routing. This is a load-aware ECMP. This is the approach that we will be using, we will be supporting with Sonic as well, and that is what I will focus on today. Finally, the incast problem is best resolved at the receiver end. A receiver knows exactly how much traffic it is receiving. A receiver can pace the senders to only send according to the capacity receiver have. So there are different credit control mechanisms available. These mechanisms can be run from the top of the rack switch, or these could be run from the endpoint itself. We at Broadcom, we have two unique architectures to meet all the AI networking requirements. What you see on the left-hand side is what we call switch-scheduled fabric. In a switch-scheduled fabric, all the congestion management, flow control, load balancing, everything is managed by the switch. That's why we call it switch-scheduled. Tomorrow, my colleague Uzi with ByteDance, with TikTok, they will be doing a presentation tomorrow at 1:30. They will be talking about that side of the solution. I will focus on the right-hand side, which is what we call endpoint scheduled. As the name suggests, endpoint need to participate here in congestion management, right? And this is the approach, as I said, we are using with Sonic as well. So here we use cognitive routing. What is cognitive routing? It is a suite of capabilities that adds global intelligence to your routing decision. It improves routing for all sorts of application, but it is specifically good for the AI application. I only got 5 minutes left, so I'll go very quick. GLB, global load balancing. This is a capability where when your switches are making decision where to hash the traffic, they do not just look at the local conditions, they look at the global conditions. They can look at the link utilization downstream as well, multiple hops away as well. They have a view of the whole topology. How do we do this magic? We run an embedded app in Broadcom Silicon. Think about it like your car GPS navigation. When you're leaving from your home to your work, your navigation knows exactly 5 roads down the road there is some issue, and they will redirect you from your very start of your journey. We bring those capabilities, those global view visibility into network with GLB, with our Tomahawk 5 family of silicon. Reactive path rebalancing, once again, very, very useful feature. Remember I talked about, we are talking about long-lived flows. Remember, flows between 2 GPUs can last for multiple weeks. So think, if you are doing static load balancing and for whatever reason, at the point when the 2 flows started, you pinned them to one particular link, and that link is now congested. Maybe network situation changes at night. Network situation changes, right? Congestion changes. Maybe a better path has now become available. With reactive path rebalancing, we are continuously looking at the better path, and if we find a better path, we will switch your heavy elephant flow to a much less congested link. So now you have 2 very happy flows doing their job. Fast link failover. In our silicon, with Tomahawk 5, we have achieved a 200 nanosecond failover. It is order of magnitude better than your standard Ethernet with 50 microsecond. DCN, don't have a lot of time to explain it, but at a very high level, DCN is basically a packet trimming feature, where what you are doing is, if a packet is dropped in the network because of congestion, you trim the packet, you take the header, and you send it in the fast queue to the receiver. Receiver will receive it very quickly, ask for a retransmission from the sender, and will get that packet. This is much faster than sender waiting for the acknowledgement timeout, and then retransmit it. You really make this process very, very fast. I'll skip this slide. Okay, so what are the enhancements we are making in Sonic? Now remember, all the things I'm mentioning here, these are either they are already available or they are coming in Sonic in this summer. So we're talking about a couple of months' time. Number 1, adaptive routing. This is the load-aware ECMP I talked about. This will be available in Sonic. Advanced hashing. We are doing 2 things here. Remember I said entropy is a big problem? What are we doing about it? Number 1, we are doing what we call UDF hashing, user-defined field. And we are looking inside the RDMA header to look at the queue pairs. What is the benefit? You get more entropy. You can get better load balancing. And number 2, we have now improved the hashing algorithm itself. We are using an algorithm called versatile hashing. It is much better in performance. It has been proving compared to your regular RTAG 7 algorithms. Congestion. So Rocky V2, you already know. We have now we are supporting Rocky V2 on Sonic. The good thing we are doing here is we made the implementation very simple. Ask anyone who has deployed Rocky, and they will tell you it is not easy to configure. You configure multiple different things. In Sonic, we made it simple. You just do one command, Rocky enable, enter. That's it. All your ECM, all your ECN, PFC, your lossless buffer configuration, everything is done. And finally, we are enabling multi-tenancy on Tomahawk 5 line of silicon. People who are aware of Broadcom silicon, they know that we do not support VXLAN on the Tomahawk family, but we are doing it in Tomahawk 5 because we see customers have this requirement to have multi-tenancy on the back-end fabric. On the AI network, they want multi-tenancy on the back-end as well. Why? Because there are customers we are talking to who want to have this GPU as a service. And to provide GPU as a service, you need to have multi-tenancy there. I'll just finish in a couple of minutes. I'm running over time. Okay. All right. So there was a couple of years back, there was a notion that probably because of its background in HPC, because of its success in HPC, InfiniBand may become a prominent player in AI networking. And InfiniBand has had its merit. when you talk about HPC and when you talk about low latency requirements. But when it comes to AI networking, it has now been proven that Ethernet beats InfiniBand every day of the week, twice on a Sunday, right? This is what you see on this slide. This shows the results of some benchmarking done by our megascaler customer, which shows that Ethernet is at least better, is providing better performance, at least 10% more performance than InfiniBand. Now you may ask me, 10% is not significant, but remember, the cost of networking in AI infrastructure is how much? 10%. So if I'm improving your infrastructure by 10%, networking is paying for itself. So second point that I want you to remember here is, there will be failures in the network. Why? The optics that we have, they are still a bit flaky, right? We see a 2% annual failure rate on optics, if not more. So, which means that if you have a 4,000 node network, you will be seeing 15 failures per month. Look at the comparison between the failover rate between Ethernet and InfiniBand. Ethernet is at least 30 times better in failover than InfiniBand. Another reason for sticking with open source technologies like Ethernet. And Ethernet is the de facto standard of AI network. Ethernet is deployed by all the megascalers, barring one that you don't see here. Everyone has deployed Ethernet. Interesting thing is Alibaba Group and ByteDance, because not only they're using Ethernet in their AI network, they are using Sonic in their AI network. Do attend ByteDance presentation tomorrow at 1:30 p.m., where they talk about their AI networking with Broadcom, Silicon, and Sonic. AI models are rapidly increasing in size. ChatGPT 3 to ChatGPT 4, we saw a 6-time increase. We are already building over 64,000 node cluster as we speak. Amazon have already built it. It's public knowledge. But now we want to be ready for the next phase of this AI networking. And for that, we are working to be ready to support 1 million node of AI. And to do that, these are a bunch of companies who have working together in Ultra Ethernet Consortium, where we are trying to improve Ethernet to support these 1 million node scale. And there are multiple things we are doing, but I'll just leave you with this, that what we are doing is we are modernizing RDMA. I'm giving you some link in this slide. Please have a look at that. There is a very good white paper available on Ultra Ethernet Consortium website that you can review, which tell you a lot of things that we are doing there. So in a nutshell, what we are saying is that networking requirements of AI infrastructure are different. We need to be aware of that. Sonic is ready to be deployed in AI world. We already know ByteDance has deployed it, Alibaba has deployed it. It is ready for AI workloads. Please get involved with Ultra Ethernet Consortium. I already gave you a link for the Alibaba presentation I was talking about. And if you want to know more about how to configure Sonic, this is my YouTube channel, Love to Network, because I do love to network. Thank you very much for your time.
Thank you, perfect. Any questions? Yeah, sure.
Sorry, difficult questions are not allowed. Did I mention?
Yeah, you were talking about Ultra Ethernet, and will future Sonic releases will support Ultra Ethernet also? Will future releases, Sonic releases, support Ultra Ethernet?
Ultra Ethernet. I hope so. I hope so. Yeah. No, it's a valid question. I appreciate that. I don't know the exact answer. The Ultra Ethernet products with Ultra Ethernet will be available hopefully by next year. So it is not something which is like 10 years, coming. A lot of work has already been done. Products with this will be coming next year. I believe it will be supported, but I can't say for sure. Yeah. Thanks for your question. Thank you, everybody.
Sorry,
Yes.
Kamran, I thought you're rushing because I know you finished, but great presentation, thank you. One question, you mentioned Broadcom Silicon. Is the solution you have offered purely done in silicon, or there is associated software also which is intelligent on top?
When you run Sonic, when you download Sonic from community and you're running it, close to half of it is Broadcom's contribution. Maybe less than that, but a lot of it is Broadcom's contribution. So you're using Sonic, you are already using a lot of Broadcom contributions here.
Which includes software as well, or just a pure silicon?
No, yeah, we do a few softwares as well, including distribution of Sonic. Yeah, you can talk to Store Disk guys about that.
Okay, thank you.